Welcome again to another training module from CloudMasters Inc. Today, we will be focusing on preparing you for AWS Solutions Architect or AWS Cloud Engineer positions. We have organized a collection of expert-level questions, along with detailed answers. This set will cover topics like cloud migration strategies, cost optimization, serverless infrastructure, API and event-driven architecture, and other AWS resources. Cloud migration and strategies. Question 1. What are the key steps in migrating an on-premises application to AWS? Answer. Migrating an on-premises application to AWS requires a structured approach that minimizes risks and ensures a smooth transition. Here's a detailed breakdown, assessment, and planning. This phase involves understanding your current environment, including workloads, application dependencies, and performance requirements. It's crucial to conduct a total cost of ownership analysis to compare the costs of on-prem infrastructure versus AWS. Application discovery tools such as AWS Application Discovery Service can help identify application dependencies and performance baselines. During this phase, assess whether applications are suitable for cloud migration and identify any required refactoring. Choosing a migration strategy, AWS recommends the 6 R's of migration strategies. Rehost or lift and shift moving applications as is to AWS without major changes. This is often a first step in migration for immediate cost savings but may not leverage cloud-native benefits fully. Replatform, a minor refactor where parts of the infrastructure are optimized for AWS, such as migrating databases to Amazon RDS or adopting managed services like Amazon Elastic Beanstalk. Refactor or re-architect. This involves significant changes to the application, often to leverage serverless, microservices, or container-based architectures, leading to better scalability and performance. Repurchase, abandoning custom applications in favor of cloud-based SaaS solutions. Retire, decommissioning applications that are no longer useful. Retain, keeping certain applications on premises, for example, due to regulatory or latency requirements. Architecting the cloud environment. Based on AWS's well-architected framework, your cloud architecture should prioritize security, implement identity and access management, encryption at rest and in transit, and logging using services like AWS CloudTrail and AWS Config. Reliability, design with fault tolerance in mind by leveraging multi-AZ deployments, AWS Elastic Load Balancer, and services like Amazon RDS and DynamoDB for high availability. Cost efficiency. Use services such as AWS Cost Explorer to track and optimize costs by utilizing reserved instances or savings plans for predictable workloads. Performance efficiency. Use auto-scaling and elastic load. Balancing to handle traffic spikes while avoiding underutilization or over-provisioning. Operational excellence. Automate monitoring and alerting using CloudWatch and use AWS Systems Manager for incident management. Migration tools. AWS Migration Hub provides a centralized view of the progress of application migrations across multiple AWS and partner solutions. AWS Server Migration Service helps migrate virtual and physical servers to AWS without requiring long downtimes. AWS Database Migration Service facilitates migrating on-prem databases to Amazon RDS, Aurora, or DynamoDB with minimal downtime. AWS Snowball and AWS DataSync allow for large-scale data migration by transferring petabytes of data efficiently. Executing the migration. Follow a phased approach, beginning with less critical applications or a pilot workload to validate your migration strategy. Leverage tools such as AWS Cloud Endure for disaster recovery during the migration phase. Ensure continuous integration of security practices through automated policies using AWS organizations and AWS Identity and Access Management to manage permissions during the migration process. Validation and optimization. Post-migration. Thoroughly test application performance using AWS CloudWatch and implement further cost optimization techniques, such as converting over-provisioned resources to on-demand or auto-scaling architectures. Perform security checks to ensure encryption, IAM policies, and audit trails are functioning as expected, and continuously monitor for anomalies using AWS GuardDuty and AWS Security Hub. Cost optimization. Question 2. How can AWS autoscaling contribute to cost optimization? Answer. AWS autoscaling is a critical feature for optimizing infrastructure costs while maintaining application performance. Here's a more expert-level explanation: right-sizing resources. Auto-scaling ensures that your resources are dynamically adjusted to handle traffic demand. For example, if your application experiences spikes in traffic during specific hours, auto-scaling will automatically add EC2 instances or other scalable resources to handle the load. Conversely, it reduces instances during low demand, ensuring you only pay for what you use. This prevents the traditional issue of over-provisioning resources, where businesses typically maintain more servers than necessary to handle peak demand, leading to inefficiencies and wasted costs. Scaling policies. Auto-scaling supports multiple policies, including target tracking. You can set a target for a specific metric, such as CPU utilization. Auto-scaling will automatically adjust instances to maintain this target, ensuring you're not overpaying for underutilized resources. Step scaling. This is useful when you need different scaling behaviors for varying levels of demand. For instance, you can define that for every 20% increase in CPU usage, one additional EC2 instance is added, making the scaling process more granular and cost-effective. Scheduled scaling. This policy allows you to predefine scaling events. For example, if you know your traffic increases on weekends, you can schedule instances to scale up just before peak traffic, minimizing the need for manual intervention and over-provisioning. Spot instances integration. You can configure auto-scaling groups to use EC2 spot instances, which can significantly reduce costs, up to 90% savings over on-demand instances. These are ideal for workloads that are flexible and can tolerate interruptions, such as batch processing or large-scale data analysis. Elastic load balancing integration. Auto-scaling works in tandem with elastic load balancing, which distributes incoming traffic across multiple healthy instances. This prevents any one instance from becoming overloaded, optimizing resource usage and minimizing costs by spreading out workloads efficiently. Cost insights with CloudWatch and Cost Explorer. By closely monitoring metrics in CloudWatch, such as CPU utilization and memory usage, you can identify underutilized instances and fine-tune auto-scaling policies to further optimize costs. AWS Cost Explorer provides insights into which services are consuming the most resources, allowing you to optimize specific instances based on performance metrics. In conclusion, auto-scaling not only helps you maintain optimal application performance, but is also a vital tool for reducing AWS costs by ensuring resources scale dynamically with demand. Serverless infrastructure. Question 3. What are the best practices when designing a serverless application on AWS Lambda? Answer. Designing serverless applications on AWS Lambda requires a thorough understanding of the AWS ecosystem and cloud-native principles. Here's an expert guide: minimizing cold starts. Cold starts occur when AWS needs to initialize a new Lambda container for an incoming request. The initialization time can vary depending on the runtime. For example, Java and .NET typically have longer cold starts compared to Node.js or Python. Best practices to mitigate cold starts include using provisioned concurrency to keep functions initialized and ready to respond to requests with minimal latency, optimizing the initialization code to only load what is necessary, and avoid heavyweight libraries unless required, avoiding dependencies with large binaries or libraries that can significantly increase startup time. Statelessness and external state management. Lambda functions should be designed to be stateless, meaning they should not maintain persistent data between invocations. Instead, use external services such as Amazon S3 for storing large files, Amazon DynamoDB for fast, scalable key-value data storage, Amazon Elasticache for in-memory caching to reduce the number of direct calls to databases, AWS step functions to coordinate complex workflows and maintain application state across multiple Lambda functions. Efficient use of resources. Adjust memory settings based on the workload. Lambda automatically allocates CPU power proportional to the memory allocated. A common misconception is that allocating less memory saves costs, but in fact, matching memory to workload size can significantly reduce execution time, thus lowering costs. Use AWS Lambda layers to reuse code across multiple Lambda functions, reducing deployment size and cold start times. API Gateway for API management. When exposing your Lambda functions to the web, Amazon API Gateway serves as an interface to manage RESTful APIs. It offers features such as throttling to protect Lambda functions from being overwhelmed by excessive requests, request validation and transformation. API Gateway can perform lightweight validation and transformation of requests, reducing the load on Lambda. Caching responses. For APIs where responses don't change often, API Gateway's built-in caching can reduce the number of times a Lambda function is invoked, saving costs and improving performance. Monitoring and observability. AWS CloudWatch is essential for monitoring Lambda function performance. Track metrics such as invocations, errors, and duration to identify underperforming functions. AWS X-Ray helps trace and debug serverless applications by visualizing the flow of requests through various services. For example, API Gateway to Lambda to DynamoDB. This is crucial for identifying bottlenecks or failures in distributed applications. Cost management. While Lambda's pay-per-execution model is attractive, careful monitoring is required to prevent overuse. Tools like AWS Budgets and Cost Explorer can help track spending, and Lambda cost optimization reports can identify functions that are using more resources than necessary. In summary, designing serverless applications with AWS Lambda requires careful attention to initialization times, stateless architecture, appropriate memory allocation, and leveraging AWS's monitoring and observability tools for continuous optimization. API and event-driven architecture. What are the benefits of using an event-driven architecture on AWS? An event-driven architecture offers several advantages, particularly when leveraging AWS services that support asynchronous communication and decoupled microservices. Here's a breakdown of the key benefits: scalability and flexibility. Event-driven architectures inherently support scaling because they react to events as they occur. AWS services like Amazon SNS, SQS, and AWS Lambda allow the system to scale seamlessly in response to varying event loads. For example, if a web application suddenly experiences a surge in user activity, you can trigger additional Lambda functions to process events without needing to provision new servers or resources manually. Loose coupling. In a traditional tightly coupled architecture, services are often interdependent, leading to complexities when scaling or updating individual components. Event-driven systems decouple the producer and consumer of events, making it easier to scale components independently. By decoupling, you can deploy new versions of a service, such as new Lambda functions, without affecting the producer or other consumers. For example, SNS can broadcast events to multiple consumers, such as Lambda functions or SQS queues, each with its own processing logic and scaling policies. Real-time processing. AWS offers several services like Amazon Kinesis and AWS Event Bridge that handle real-time event ingestion and processing. This is especially important in applications requiring immediate responses, such as IoT data collection or real-time analytics. With Kinesis data streams, you can build pipelines for processing real-time data with ultra-low latency, making it ideal for use cases like fraud detection, live content streaming, or gaming analytics. Reduced latency and higher availability. EDA leverages asynchronous communication between components, which reduces the latency associated with waiting for synchronous API calls to complete. By sending events that can be processed later, the system remains responsive, even under heavy load. AWS services like SQS provide automatic message durability, meaning that even if a consumer fails, the message remains in the queue until it's successfully processed, improving overall availability and fault tolerance. Cost efficiency. Event-driven architectures can be more cost-efficient than traditional approaches because you pay for resources only when events are being processed. Services like Lambda follow a pay-per-execution model, where you are charged only for the duration of the function execution and not for idle resources. Event queues like SQS enable message decoupling, ensuring consumers process events only when necessary, reducing the risk of idle or over-provisioned resources. Integration with cloud-native services. AWS. EventBridge is a powerful service that facilitates the integration of applications across AWS accounts, SaaS platforms, and on-premise systems. You can use EventBridge to define rules that automatically respond to state changes in services like AWS Step Functions, EC2 Autoscaling, or AWS Systems Manager, allowing for fully automated event-driven workflows. Amazon S3 event notifications, for example, can trigger Lambda functions, SNS notifications, or SQS messages upon changes, such as new object creation, enabling flexible, event-driven automation of data workflows. In conclusion, event-driven architectures in AWS provide a highly scalable, decoupled, and cost-efficient way to handle dynamic workloads and real-time data processing, making them ideal for modern cloud-native applications. AWS Resources. What are the best AWS resources to leverage for building fault-tolerant, highly available architectures? AWS offers a rich ecosystem of resources and services to help architects design highly available and fault-tolerant systems. Here's a detailed look at the most critical AWS resources to achieve this goal. Amazon EC2 Autoscaling. Autoscaling ensures that your application maintains optimal performance and cost efficiency by automatically adjusting the number of Amazon EC2 instances based on demand. By integrating with Elastic Load Balancer, autoscaling distributes traffic across healthy instances, preventing performance degradation. Additionally, autoscaling supports multiple availability zones, ensuring high availability across AWS regions. In the event of an instance or AZ failure, autoscaling launches replacement instances in other AZs, maintaining application availability. Elastic Load Balancer. Elastic Load Balancer automatically distributes incoming application traffic across multiple EC2 instances, containers, or Lambda functions. It supports load balancing across multiple AZs, ensuring high availability by routing traffic to healthy targets only. ELB also integrates with AWS Global Accelerator, which enhances availability and performance by leveraging AWS's global network to route traffic to the nearest healthy endpoint, reducing latency and improving fault tolerance. Amazon RDS Multi-AZ Deployment. Amazon RDS provides a managed database service, and its multi-AZ deployment feature ensures enhanced availability by automatically replicating your database in multiple availability zones. In the event of a failure in the primary database, RDS automatically performs a failover to a standby instance in a different AZ, minimizing downtime and data loss. This feature is critical for applications that require strong consistency and high availability. Amazon Route 53. Amazon Route 53 is a highly available and scalable domain name system web service that routes end-user traffic to AWS resources. Route 53 is essential for achieving global high availability, as it enables geolocation routing, latency-based routing, and health checks. With Route 53 health checks, you can continuously monitor the health of your application endpoints and automatically failover traffic to healthy endpoints when necessary. It also supports routing policies such as weighted routing, allowing traffic distribution based on assigned weights for each endpoint, ensuring resilience across AWS regions. Amazon S3 Cross-Region Replication. Amazon S3 is designed for 11.9's durability of objects and offers built-in redundancy by storing data across multiple AZs. For enhanced disaster recovery, cross-region replication can be used to automatically replicate S3 objects to a different AWS region. This ensures that even in the event of a regional failure, your data remains accessible from the replicated region, providing both fault tolerance and high availability for mission-critical applications. Amazon DynamoDB Global Tables. Amazon DynamoDB offers Global Tables, a fully managed multi-region, multi-master database solution that provides automatic replication of data across AWS regions. This allows your application to remain globally available, even in the event of regional outages. DynamoDB Global Tables ensure low-latency reads and writes for distributed applications while maintaining eventual consistency across regions, which is essential for global high-availability architectures. AWS Global Accelerator. AWS Global Accelerator improves the availability and performance of your global applications by using AWS's global network infrastructure to route traffic to the nearest available application endpoints. It detects endpoint health in real time and automatically reroutes traffic to healthy endpoints in different AWS regions if any endpoint fails. This service significantly reduces the latency for users by routing them through the AWS backbone rather than the public internet, and provides fault tolerance by ensuring that traffic is only routed to healthy endpoints. AWS Backup and AWS Disaster Recovery. AWS Backup allows centralized management of backups for a variety of AWS resources, such as EC2 instances, EBS volumes, RDS databases, DynamoDB tables, and more. With automatic backup schedules, retention policies, and encryption, AWS Backup ensures that critical data is protected and recoverable in case of failure. For disaster recovery, AWS offers services like CloudEndure Disaster Recovery, which provides near real-time continuous replication of workloads across AWS regions, enabling fast failover and recovery in case of a catastrophic failure. By leveraging these AWS resources, architects can design systems that are both highly available and fault-tolerant, ensuring minimal downtime and enhanced resilience across regions and AZs. Cloud migration and strategies. How does AWS Direct Connect support hybrid cloud migration strategies? AWS Direct Connect is a dedicated network connection that helps businesses build hybrid cloud architectures by providing a high-bandwidth, low-latency link between on-premises data centers and AWS. Here's how it supports migration: low-latency, high-bandwidth connectivity. Direct Connect provides a private, dedicated connection bypassing the public internet. This ensures low latency, higher throughput, and consistent network performance, which is critical for moving large volumes of data during migration. Enterprises can provision bandwidths from 1 Gbps to 100 Gbps based on their migration needs, secure data transfers. Unlike typical VPN connections that traverse the public internet, Direct Connect offers a private, secure link between your data center and AWS. This reduces the risk of data exposure during migration, especially for sensitive workloads. It integrates seamlessly with AWS Transit Gateway for managing hybrid connectivity across multiple AWS accounts. Hybrid cloud workloads. Direct Connect is often used in hybrid cloud strategies where workloads are split between on-premises infrastructure and AWS cloud. For instance, businesses may retain sensitive applications in their data centers while migrating less critical services to AWS. With Direct Connect, these workloads can interact with minimal latency, enabling seamless hybrid operations. Use with AWS Storage Gateway. AWS Direct Connect can be paired with AWS Storage Gateway to simplify the migration of data from on-premises storage systems to AWS. Storage Gateway can cache on-premise data locally while replicating data asynchronously to Amazon S3, Amazon Glacier, or EBS, ensuring data integrity during migration. Data replication and migration tools integration. Direct Connect is commonly used with AWS Database Migration Service and AWS Snowball to replicate and migrate databases, ensuring fast, reliable, and secure transfers of data from on-premises systems to AWS. By enabling a stable, high-performance connection, Direct Connect minimizes data transfer costs during migration while improving the reliability of the transfer process. In summary, AWS Direct Connect is a vital component of hybrid cloud migration strategies, providing fast, secure, and reliable connectivity between on-premises environments and AWS. Are you ready to ace your AWS Solutions Architect interview? Go into your interview feeling confident and show your best personality. In another module, we would be looking at behavioral interview questions and how you should approach them. Until next time, all the best from CloudMasters Inc. Please like, share, and follow for more contents to help you on your IT journey.